Hello, this is Tim Smith, the Academic Support Coordinator of St. John's River State College, St. Augustine campus. This lesson, the cross product, is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. It is recommended to view the videos Introduction to Vectors and the dot product prior to watching this video. In this video, we will discuss the definition of the cross product, orthogonality, algebraic properties of the cross product, determinants, and geometric properties of the cross product. If V equals V1I plus V2J plus V3K, and W equals W1I plus W2J plus W3K are two vectors in space, the cross product V times W is defined as being equal to the quantity of V2 times W3 minus V3 times W2I minus the quantity of V1 times W3 minus V3 times W1J plus the quantity of V1 times W2 minus V2 times W1K. The way the cross product is developed, it can be shown that the cross product of V times W is orthogonal to both V and W. We start with the definition of the cross product V times W. Taking the dot product of V times this cross product gives us V1 times the quantity of V2W3 minus V3W2 minus V2 times the quantity of V1W3 minus V3W1 plus V3 times the quantity of V1W2 minus V2W1. Distribute the parentheses. V1 V2W3 cancels with negative V2 V1W3. Negative V1 V3W2 cancels with plus V3 V1W2. And V2 V3W1 cancels with negative V3 V2W1, leaving a final answer of 0. The same solution is achieved with the dot product of W and the original cross product. The dot product is set up the same way as before, then distribute the parentheses. In this case, W1 V2 W3 cancels with negative W3 V2 W1. Negative W1 V3 W2 cancels with positive W2 V3 W1, and negative W2 V1 W3 cancels with positive W3 V1 W2. This leaves 0, proving the cross product of U times V is orthogonal to the plane created by U and V. For example, find the cross product of the following two vectors. V equals negative I plus 2j plus 5k, and W equals 4i minus 3k. We start with the definition of the cross product and fill in the values and simplify to get negative 6i plus 17j minus 8k. Next, we showed that the cross product of V times W is orthogonal to V, so the dot product of V times the cross product of V times W is negative 6i plus 17j minus 8k times negative I plus 2j plus 5k. This gives us 6 plus 34 minus 40, which equals 0. The following are algebraic properties of the cross product. If U, V, and W are all vectors in space, and if A is a scalar, then the cross product of V times V equals the 0 vector. The cross product of V times W equals negative the cross product of W times V. A times the cross product of V times W equals the cross product of A times V and W, which equals the cross product of V times A times W. The cross product of V times the quantity of W plus U equals the cross product of V times W plus the cross product of V times U. The magnitude of the cross product of V times W squared equals the magnitude of V squared times the magnitude of W squared minus the dot product of V times W squared. The dot product U times the cross product of V times W equals the cross product of U times V times the dot product of W. A determinant is a scalar-valued function of the entries of a square matrix. The determinant of a 2 by 2 square matrix containing A, B, C, and D is A times D minus B times C. The determinant of a 3 by 3 square matrix containing A, B, C, D, E, F, G, H, and I is equal to the 2 by 2 square matrix E, F, H, and I times A minus the 2 by 2 square matrix D, F, G, and I times B plus the 2 by 2 square matrix D, E, G, and H times C. This also equals A times E times I minus A times F times H minus B times D times I plus B times F times G plus C times D times H minus C times E times G. Determinants can be a convenient tool for solving the cross product of two vectors. We can start with the definition of the cross product of vectors v and w. We then fill in the 3 by 3 square matrix with I, j, and k in the top row, the values for the v vector in the second row, and the values for the w vector in the third row. This will result in 3 2 by 2 matrices that can be more easily solved. For example, let the vector v equal 5i plus 2j minus k, and the vector w equal to negative j plus 4k. In the 3 by 3 matrix, we fill in the top row with I, j, and k, the second row with the values from v as 5, 2, and negative 1, and the third row from vector w, 0, negative 1, and 4. This leads to 3 2 by 2 matrices, 2, negative 1, 4, I, minus 5, negative 1, 0, and 4 times j, plus 5, 2, 0, and negative 1 times k. Solve these matrices to get 8 minus 1i, minus 20 plus 0j, plus negative 5 minus 0k, or 7i minus 20j minus 5k. If v and w are two non-zero vectors in space, then the cross product v times w is orthogonal to both v and w. The magnitude of the cross product of v times w equals the magnitude of v times the magnitude of w times sine theta, where theta is the angle between v and w. The magnitude of the cross product of v times w is the area of the parallelogram having v and w as adjacent sides. The cross product of v times w equals the zero vector if and only if v and w are parallel vectors. And the absolute value of the dot product of u times the cross product of v times w is the volume of the parallelepiped having u, v, and w as adjacent sides. Find the area of the parallelogram with one vertex as p and sides pq and pr, where the point p is 1, 1, negative 6, q is 5, 3, 0, and r is negative 2, 4, 1. The area of the parallelogram is found by taking the magnitude of the cross product of the vectors v times w. We first start by establishing the vector v as the vector from p to q, which is solved by 5, negative 3, 0, minus 1, 1, negative 6, which results in the vector 4, negative 4, 6. The vector w we establish as the vector from p to r, which is solved by negative 2, 4, 1, minus 1, 1, negative 6, which results in the vector negative 3, 3, 7. The cross product v times w can be solved using the 3 by 3 matrix determinant. We set the top row as ijk. The second row will be the values of the vector v, 4, negative 4, 6, and the third row will be the values of vector w, negative 3, 3, 7. This equals the 3 2 by 2 determinants, negative 4, 6, 3, 7 times I, minus 4, 6, negative 3, 7 times j, plus 4, negative 3, 3 times k. This equals negative 4 times 7, minus 6 times 3 times I, minus 4 times 7 minus 6 times negative 3 times j, plus 4 times 3 minus negative 4 times negative 3 times k. This simplifies to negative 46i minus 46j. The magnitude of this vector equals the square root of 46 squared plus 46 squared, or 46 times the square root of 2 square units of area. Find the volume of the parallel pipette whose adjacent sides are the vectors u, v, and w, where u equals 8i minus 6j plus 5k, v equals 2i plus 3j minus 8k, and w equals I plus 6k. The volume of the parallel pipette is the absolute value of the dot product of u times the cross product of v times w. We'll start with the cross product of v times w, which equals the 3 by 3 matrix determinant with I, j, and k in the first row, 2, 3, and negative 8 in the second, and 1, 0, 6 in the third. This equals the 2 by 2 matrices 3, negative 8, 0, 6 times I, minus 2, negative 8, 1, 6 times j, plus 2, 3, 1, 0 times k. We solve the 2 by 2 determinants to get 3 times 6 minus negative 8 times 0 I, minus 2 times 6 minus negative 8 times 1 j, plus 2 times 0 minus 3 times 1 k. Simplify to get 18i minus 20j minus 3k. We take this vector and take the absolute value of the dot product of u times this vector, or 8i minus 6j plus 5k times 18i minus 20j minus 3k. This equals the absolute value of 8 times 18 minus 6 times negative 20 plus 5 times negative 3, which equals the absolute value of 144 plus 120 minus 15, or a final answer of 249 cubic units of volume. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you, and good luck with your studies.